I've been working on a way to compress atmospheric data into its real information content. And this is a project that actually already started last year. Basically this year's ECMWF weather code project is kind of the follow-up of what happened last year. And so I really want to use this opportunity to give everyone like a hopefully intuitive introduction to what real information content means and how that actually can be used for data compression. So when we talk about data compression, we usually think of some kind of a trade-off between size, speed, and precision, meaning that you ideally, because that's the idea of data compression, you want to end up with some data that is smaller than what you had before without actually throwing away too much information. You kind of want to still get a very good picture of what you started with. And this transformation from the original data to your compressed data should also happen in a reasonably fast way. So meaning that the compression speed shouldn't, exceed a certain level, as well as the decompression speed. So basically regain your data from whatever format you squeezed it in. And many of us basically almost every day use some form of data compression. So for example, if you take a picture, what actually happens is that the sensor of your camera takes a picture, has a lot of information, and then if you use something like JPEG, what actually JPEG does is it basically throws away all the colors that your eye can't see anyway. And so you basically restrict the information to like a restricted, smaller color space. If you listen to music, for example, then this whole MP3 encoding basically means that you throw away the information that a human ear can't hear anyway. And so basically what we try to do is to find an equivalent for climate data so that we keep the information that is real and that we throw away the false information. So the information that, for example, if you provide a forecast or if you analyze the data in order to understand climate change better, that you keep that, but you throw away the unnecessary, fake information in your data. We've applied this idea to the Copernicus Atmospheric Monitoring Service CAMS that we've already heard about in the last talk. So we have more than 60 atmospheric variables. So there's things like nitrogen dioxide, ozone, and so on, and a lot of aerosols. And you just see two pictures here of what this can look like. So there's a lot of different physical processes involved. You see ship tracks in the very bottom in nitrogen dioxide at the surface, but you also see a lot of like turbulence and mixing. You can even see like impacts of solar radiation on the nitrogen dioxide levels. And in general, ECMWF produces data at about 200 terabyte every single day. So that means every second there's 2 gigabytes of data produced in ECMWF's archive. So this will even quadruple if we go towards a 1 kilometer global resolution model, and CAMS of that archive only, let's say, a small section, which produces about 600 gigabyte every day. But we basically use it in order to understand how can we compress this data better to reduce the stress on the data archive, and therefore facilitate data sharing. It's much easier to download 1 gigabyte instead of 10 gigabyte. And so what we mean if we talk about information preserving compression, first step, you have some kind of gridded data. That, for example, could be on a LED long grid, that could be on any other kind of grid. And once you have this data, what actually happens, because all this data is stored in zeros and ones, they're usually stored in floating point numbers. Floating point numbers is the idea that instead of storing a real number at a certain precision, you basically split the whole thing up into a sign. So you have a sign bit either being 0 or 1, depending on what sign the number has. You have an exponent that tells you whether you have a very large or very small number. And then you have the mantissa bits, and the mantissa bits basically describe what are the decimal digits behind the dot. And the idea is that you basically look at every single of these bits for every number on your whole gridded data set, and you investigate what, for every of these bit positions, what are the adjacent bits in the adjacent grid points, the bits in the adjacent grid points. So for example, for the sign bits, you see, all of them are zeros. For the 5th x1 bits here, for example, you see like, oh, these ones are all 0, but other ones are 1, and so on and so forth. And you basically compare them. And this is basically then using information theory. And information theory can tell us more about what the mutual information between all of these bits is. So for example, if all of the adjacent bits are all 0, they're all identical, then there's no mutual information because there's no information to start with in the first place, because you basically already know it's all zeros, so there's no need to actually encode more. However, if 0 is certainly adjacent to another 0, and 0 and 1s occur equally frequent, which I've tried to illustrate here, then your mutual information is 1, meaning that if you already know that a given bit is 0, you have already a very good predictor for that the surrounding bits are also 0, and the same counts for 1. And this basically, you can play this game for all of the single bits, and then you obtain an information for every single bit position. And this is what this looks like then. So if we take our number, we represent it in the sign exponent multiplicity representation, and then you basically get an amount of real information ranging from 0 to 1 in your data set, and you can basically isolate the false information in your data. So instead of representing the number here, for example, 1.23 and so on and so forth, as these bits, we actually realize, oh, we don't need to store the last bits here that are marked in purple. And actually, it would be much easier if we remove this false information, because this would facilitate data compression. Because you basically don't have to store all these zeros and ones at the end, because they're completely statistically independent, really hard to compress anyway. And so the idea is that you basically throw this information away, the false information, and you retain the bits that actually preserve most of the real information in your data set. And yes, we've basically are now trying to implement this in all its little details. This is an example, what I've come up quite recently, where we basically tested the same approach on satellite data. So if you look here closely, you may be able to recognize Turkey and the Mediterranean, as well as the Black Sea. And this is just a satellite picture from a given day. And now the question is, one of these pictures is based on the original data containing the full precision, and the other one has been compressed with this information preserving compression. And question, can you see the difference? I'll give you 5 seconds, but I guess you won't be able really to see the difference. However, one of them is about 15 to 20 times smaller than the other. And the result is actually the one on the left is the compressed one, and the one on the right is the original one. And so actually, if we were to store everything about like 20 times smaller, the stress on the data archive would be much reduced. It would be much easier to download this data, and so on and so forth. And in order to explain this a little better, this is a picture here created from water vapor using the CAMS data set. So basically, if we preserve 100% of the information that's shown here on the left, this is what this water vapor looks like over the globe. And then if you go into the next slice here, then we basically throw away 0.1% of the information, but suddenly our compression factor really increases. And you basically then end up with a trade-off between size and information, and not precision, as I've introduced in the beginning. And so you can basically look for one of these like sweet spots here. We usually find like throwing away 1% of information is a really good sweet spot, where you get a really big compression factor, but you retain most of the information. And if you exaggerate it a little bit, you get really high compression factors, but you can also see that suddenly there's compression artifacts appearing. If you're interested to learn more about this, because we started already last year on this project, there's already a preprint available, so you can basically click on this link. I'll also share this link in the chat. We have this article currently in review, and you also find more about this on our GitHub repositories, so ESoC/Elefridge.jl. And this also, the whole development led to a couple of other outsourced packages. So there's bitinformation.jl, which basically calculates the bit information as I've shown before. And then there's other things like ZFP compression, Lindog quantization, and so on and so forth. And they all contain more information about how we do this.